Now on to something a little more exciting. So let's say we have a region enclosed by this parabola and the x-axis, and it's revolved around the line x equals -1. So we have a nice little picture here. And it kind of looks like a bundt cake. So how would we slice this region? So since we're always talking about perpendicular, if we wanted to slice it, it does look like a washer shape down there. But if we were going to slice it that way, how would we get this radius? We can't just plug it into a function because we'd have this y value and this y value. And then the inner radius, or I said that y value, I meant x value. We have this and this. So we couldn't really do that. And we're talking about a slice, a dy slice, so we need this in terms of y. Whoops. Is that something that's easy to solve for there? Can we solve that easily for x? So we came across a problem where it might not make sense to use the perpendicular method. Okay, instead, we're going to be doing we're going to be making these shells here. And shells is a weird name, okay, not like seashells. Here's what we can think about. Think about like a roll of toilet paper, right? And so we could take the outer layer out, and that would make this shape. So we'd have like a really thin, like infinitely thin cylinder. And we could take one that would be right there. Okay, so we'd have like a smaller cylinder shape. Okay, and so it's like we have this toilet paper roll, and we're taking the outer layer off, and we're taking the next layer, and then the next layer, and the next layer. And so we have these cylinder shapes here. Okay, so do you remember how to find the surface area of a cylinder? And it's an infinitely thin cylinder, so we don't have to worry about like a big radius minus a little radius to get the whole. It's so thin we don't even have to worry about it. So we would have the 2 pi r for the circumference times the height, because we don't need the top and the bottom, those are empty. Okay, so now we have that idea. Let's see if we could figure this out. Actually, I'll leave them up there. All right, so if we wanted to find the radius, let me go in the same format that I used last time. The area is equal to 2 pi RH, okay? R, how do we figure out what that is at each of these slices, you know, or if we did a cylinder maybe from here, how do we figure out what that is? All right, well, it's whatever this x value is to 0 and then to -1. If we wanted it here, it'd be this x value to 0 and 1. So we're just doing x plus 1. Our h value, how do we find our height? Whoops. Our height is going to be given by the y value. And to get the y value, we have this 3x minus x squared. Okay, so the volume is 2 pi, the integral, r times h, and we just need to figure out our bounds. So we're going from x equals 0 all the way to x equals 3. And we want all of those cylinder shapes in between there. Okay, so we could do this, we could expand this out, but just for the sake of time, you get 70.685, or if you do go ahead and do the work, which I did in my notes, you get 45 pi over 2. All right, so let's look a little more into this. It's called a shell because it's a cylindrical shell that we're using. And it rhymes with parallel if we say parashell, so it kind of helps. So this time, the axis of rotation needs to be parallel to each little region. All right, and this formula is specified, just like we were talking about. So when you do the volume, we have different ideas of how we want to do it. You have to decide how you want to slice it. You know, is it going to be vertically or horizontally? And then is it a disc or a washer? Or would it be easier to have a shell? Okay, so let's look at an example. Okay, so we have this x squared plus 1, y equals 0, x equals 0, and x equals 1. Okay, so let's clear some of that out that we don't need. Okay, so let's think about how we want to slice this. We could, well, I guess let's figure out what it looks like. I don't like how that, all right, so, you know, it's going to have these discs at the bottom where it's full. But then up here, we would have washers. So we have two ways that we could do this. We could do from here to here, it could be a nice full cylinder. And then we have a bunch of washers. So the hole would start not too big, and then it would get bigger, and then it would get bigger until it was skinny. So we could do a part where we would do perpendicular, and then we could do perpenwashular, but we need this in terms of solve this for x. Okay, so that seems kind of complicated, or we can unravel it and instead do parallel to our axis of rotation, and we can just make these cylindrical shells. Okay, so I'm going to go with that method. So the area, I don't know why I'm putting surface area, let's just do area here. 2 pi RH, the radius. And in this case, it's pretty simple. It's just given by x. And the height is given by the y value, which is x squared plus 1. So we set up our volume, 2 pi. People always forget that 2 pi. We're going from an x value of 0 to an x value of 1. R times h. All right, so this one shouldn't take too long here. I'm going to simplify before integrating. Could have also done, you know, pattern recognition or substitution. Evaluate that from 0 to 1, 2 pi. We have 1/4 plus 1/2. This is 3/4 minus 0. So 3/4 times 2 is 3/2 pi. Nice. Okay, so we're going to be kind of looking at shapes a little bit differently, because what if they're not revolved around an axis? All right. So remember, we can take these faces and just add up the area of each of these. So what we're doing this time, this is a good example here. Imagine you have a concrete slab that's been poured, and upon that slab, walls are built perpendicular to it. So let's maybe draw a picture. I don't know. All right, here's our concrete slab. And maybe these walls that we're going to build, maybe, that's kind of a boring slab. We want to make it more exciting. It is calculus, right? So maybe our slab looks like this. Ooh. I don't know why you would pour a slab like that, but who knows? All right, so maybe on top of it, we would have rectangle walls. So there's a rectangle. This part would be like a tiny little rectangle. And then there's a rectangle. And there's a rectangle. So you see we have all these, a whole bunch of rectangle walls that we're going to put up. And there's a rectangle. But maybe instead of rectangles, we decided we wanted semicircle walls because it's exciting, right? So we'd put up little semicircle walls on top of this. You know, something like that. Or maybe we want triangular walls. right triangle walls, to be precise. Okay, it's really hard to draw in 3 dimensions. I'm not the best at it, but it'll suffice. Okay, so we have all these right angled triangles being built up from that. So this is kind of how we're doing it. We have a region, and we're going to find the area of each of these little slabs, these walls that are built up on the slab. I think it's best just to start with an example here. All right, so find the volume of the solids whose bases are bounded by the graphs of, get a nice graph here. So we have y equals x plus 1, x squared minus 1, okay, and the cross sections are going to be perpendicular to the x-axis. So they're going to be something like that. All right, identify the region that'll be the base. So do I know how to highlight that? There we go. This is our region right here. Find the points of intersection. Okay, so where does, let's get back to the pen. Where does x plus 1 equal x squared minus 1? Let's move everything to one side. So we get x squared minus x minus 2. So that'd be x plus 1, x minus 2. So they intersect at -1 and also 2. Okay, so now find the points of intersection defining the region, then write an equation s of x. We're going to use this many times. S of x equals the side length of each cross section. So that would be from here to here. So that would be our top function minus our bottom function. Whoops. And to simplify that a little bit, we'd get x plus 1 minus x squared plus 1. And some of you might not like it because I'm writing it in the opposite order that you normally do, but I'm going to leave it like that. So for each side length, we're going to use this equation. That's the side length here, or here, or here, or here, or here. Okay, that's the side of each of these shapes. So for our first, whoa, too many. For our first house or set of walls that we're going to be building, pink, why not? We're going to build squares. So how do you find the area of a square? Well, the area is just the side squared, right? So let's say if we had this, we'd have that. Oh, that doesn't look too good, but you get the idea. Here's a bigger square wall, and here's a little tiny square wall, and we're going to build this. We're going to fill that up with squares. Okay, S is given by this. So for each of these, we're going to set up how we would find the volume. So the area of a square is side squared. We're going from what, -1 to 2. The side is given by 2 plus x minus x squared. Side squared for a square. And that's your volume. All right, let's see. Rectangles with a height of 2. So base times height, 2 times, and the base is given by s. So this time we have these little rectangles, and each height is 2. So a height at 2, height at 2. So we have rectangles building on top of that. So the volume would be from -1 to 2, 2 times s. Oh, this time the rectangle, the height is 5 times the base. Well, the base is given by s, base times height, 5s. So the area is 5s squared. So the volume's pretty simple. Going from -1 to 2, 5 times s squared. Oops. All right, let's think about a quarter circle this time. Well, there. Sure, that's good enough. So the area of this is 1/2 pi, not 1/2, 1/4 pi r squared. And our radius is given by this, which is s. So it's really 1/4 s, 1/4 pi s squared in our case. So our volume would be given by this integral. Pi over 4 times s squared. 2 plus x minus x squared. All right, this one's a little different. We have semicircles. So the area of a semicircle is 1/2 pi r squared. But our function, since we're going to be building semicircles on the top, let me see, so this would look like this, or like this, or like this. Instead of building semicircles on the top, so the top, this would be our S. Well, that's the diameter. So in order to get the radius, that's S over 2 squared. All right, but we want to deal with it the least amount of work as possible. So that's pi over 2. If we square that, that'd be 1/4 s squared. So our equation really is going to be pi over 8 s squared. All right, let me clean this up. So then our volume is going to be given by pi over 8 s squared. All right, we have 3 more to go, but I would like you to try these. These are all triangles. Try to draw the picture and see if you could get the equation of the area for each of these. All right, that's it.